These notes are in section 2.2 about histograms. So a histogram is a graphical representation of a frequency distribution. It consists of adjacent vertical bars of equal width, which you can see in some of the pictures that are up here, corresponding to the class width, and heights that correspond to the frequencies. So again, you can see that here. So first, what I've done is shown the same information, and you might recognize this. This was information that we referenced in the notes from 2.1, where we talked about the daily commute time in Los Angeles. And here we have the frequency, so how many of those commute times were between 0 and 14 minutes. In the data set, there were 6 of the times that were between 0 and 14 minutes. Between 15 and 29 minutes, there were 18 data points that were between those time frames, and so on. And then over here, we have a relative frequency histogram, which is just the percentage. So it tells you what proportion of the data using percents is between those two time frames. And if you look at the histograms, they look identical. The only difference is one has the frequency, so it has the number out of the total that is within that same time frame. And then over here it would be the percentages, so you can see that kind of proportion out of the total that is dedicated to that time frame. You'll notice as well that while the class width is a width of 15, and the lower class and the upper class are 0 and 14. We don't see the 0 and 14 labeled. We do see that the difference between the labels is a distance of 15, so we can see that the width is a width of 15. However, what they did with the labeling is they labeled using the midpoints. So the middle of 0 and 14 is 7, the middle of 15 and 29 is 22, and so forth. And that's how traditionally we're going to be labeling histograms, though not all histograms are labeled that way. So that would be something special to make note of, that when we draw histograms, we're going to use midpoints down there. All right, so next we're going to look at some common distribution shapes. The first we talked about in 2.1, which is a normal distribution. This is approximately bell-shaped. You can see here's a bell shape right here. It's symmetric about the center. So there's the center, and then you can see that it's got pretty decent symmetry. This one's not perfect. And then some example would be weights of people, animals, heights, IQ measures. If you think about heights of people in the world, you've got very, very short people, you've got very, very tall people, your basketball players, but the majority of people are somewhere within this kind of average range. And so that's what you're going to see if you looked at all the people in the world and their heights, they would kind of follow this bell curve. Next is a uniform distribution where every value occurs with the same frequency, and it kind of gives you this rectangular shape. So for example, rolling a die, you have 1, 2, 3, 4, 5, and 6, and each of them have an equal chance of being rolled. So if you were to sit there and roll a die 100 times and then make a frequency table and draw a histogram from it, you would end up with your data looking something like this. Okay, next. We have bimodal distributions where you have two non-adjacent values that occur more frequently than any other value. So you can see there's two different peaks here. The occurrence of Hodgkin's lymphoma, you would see between 20 and 29-year-olds and between 70 and 79-year-olds. And here the picture that I have is actually not for this specific example, but for this specific example, you would see something that kind of looks like that. I took this from something else because they didn't have a picture I could use here. So, but this is exactly what it would look like. And it would just be something like this particular disease that is common in two different age groups. So one might be more age related and one might be genetics or something of the sort. Next is skewed distributions, and skewed distributions have a tail on one side. So here we would call this the peak, here we would call this the tail, and the skew is named after the tail. So this would be skewed to the left. This one over here would be skewed to the right. And the way that this works is the skew is the outliers. It represents the outliers. And so an example of this is American family income is skewed to the right. So you have all the incomes in America right here. You have people who are not making a lot of money, people who are kind of in the middle class, people who are kind of in the upper class, something kind of like this. And then you have your CEOs, your billionaires, you have your people who are making outrageous amounts of money, and there's a handful of them. They're skewing the data to the right, but they're certainly not the norm. They're outliers that are pulling, maybe if you were to find the average income in the United States, they might be pulling that average up instead of balancing it out. So that's what it looks like. And the skew is not looking at the peak. This is the peak right here. The skew is not named after the peak. It's named after the outliers. It's the part of the graph that's pulling, and that we call this the tail. So the peak and the tail. All right, so let's look at this. This is a problem in your book, and we're going to answer some of the questions on it. So the first question says, what is the approximate number of quarters depicted in the 3 bars farthest to the left? So here, 5, 10, I'd say this is maybe 12 quarters. We've got the weights of quarters, 25-cent pieces, quarters, how much they weigh in grams. So this is probably about 12 different weights, different quarters represented. This bar I would say is 20. And then this bar, I'd say that's about 8. So the 3 that are farthest to the left would be 12 plus 20 plus 8. That's 20 plus another 20. So there are 40 quarters represented in this data right here. What is the total number of quarters that were studied? The second question. So we'll just have to add up these over here. So this to me looks like 5. This over here less than 20, maybe 18. This one, maybe 13. That one, just a little bit less than 5, probably 4. So we've got 5, 18, 13, and 4. 18 and 13 is 31, plus 9 is 40, that's another 40. So altogether, that gives you 80. So 40 quarters over here, 40 quarters over here. This is a binomial distribution. It's actually the same picture I used up here. What is the class width? Now, before we move on, this is not the greatest graph. There's just not a lot of graphs in this particular section that I could have used for this. But this is not a great graph because if we were to do the lower class and the upper class, we can see that from one class to the next class, they're sharing numbers, which isn't really how we learned how to do a frequency distribution. So this isn't a great example of a histogram. They labeled kind of differently. They didn't use the midpoint to label, but it's what we've got. So we're going to do our best to answer the questions, and just know that if we were to draw our own histogram, we're going to kind of mimic this histogram a little bit more, where we use the midpoints than we would to kind of mimic this one. So the class width, you can tell that the width is 1/10. It's 0.1 from 5.5 to 5.6. So the width is 0.1, or you could say 1/10. What are the lower and upper class limits of the bar farthest to the left? So they only had us do the first one, which is kind of nice. It would have been confusing if we did the rest. 5.5 to 5.6. The next one would have been 5.6 to 5.7, and I was saying that's kind of the weird part, because if you recall from the 2.1 notes that we did, when you do the class widths, you don't usually recycle the number, you go to the next number, and so that makes this one a little bit confusing. But we can at least answer those questions. How would the shape of the histogram change if the vertical scale uses relative frequencies expressed in percentages instead of frequency counts shown here? Well, we can tell from the first page of the notes that if you do frequency counts versus percentages, the graph doesn't look any different. All that changes is the notation along the y-axis to say the actual count of frequency versus the percentage of the frequency or the proportion of the whole set of data. So over here I'm going to say the shape wouldn't change. The y-axis values, however, would change, and they would change to percentages. How would the shape of the histogram change if the vertical scale uses cumulative frequencies instead of the actual frequencies? So if we did cumulative frequencies, we would say quarters with the weights between 5.5 and 5.6 is 12 quarters. Then the next we would say quarters with the weight of 5.5 to 5.7 would be 32 quarters. Then we would say quarters with the weight of 5.5 to 5.8 would be 40 quarters, and then 5.5 to 5.9 would still be 40 quarters, 5.5 to 6 would be 40 quarters, and then 5.5 to 6.1 would be 45 quarters. So that's where you continue to tally up and add the numbers together and use kind of this as the lower class, but use this as the upper class, and then this is the upper class, and then this is the upper class. So how would the shape of the histogram change? We would say that the height of the bars would increase or stay the same. So as you went from this first bar, second bar, third bar, the heights would increase, and then here they would stay the same, and then increase. And then the y-axis values wouldn't be percentages, they would still be frequency, but they would be between 0 and 80. Because when you got to the final bar, you would be including all of the quarters, and there are 80 of them total. All right, what is a reasonable explanation for the gap between 5.5 grams and 5.8 grams? So why is there a grouping of quarters that are within these kind of weights, and why is there another grouping of quarters within these weights? And if you know a little bit about coins, you might be able to kind of predict this. But there is an appendix in the back of the book, I believe it's Appendix B, that says where this data came from. And in the back of the book, I put a picture of it, a screenshot. It's data set 40, and it talks about coin weights. And they had pennies, different pennies when they were made different years. Indian pennies, wheat pennies. We're not talking about that. We're talking about the quarters. And what we notice is that the quarters have two different sets of years. There are pre-1964 quarters and post-1964 quarters. And what we learn is that the pre-1964 silver quarters are 90% silver and 10% copper. The post-1964 quarters are made with copper-nickel alloy. So they're just made from different materials, and it's just the ones that were created before 1964 were made one way, and the ones after 1964 were made another way. So we'll say the reasonable explanation is that after 1964, quarters were made with different materials. Okay. All right, so we're going to draw a histogram for the frequency distribution that we used for the 2.1 notes. And this was, I don't even remember what the information had to do with. I'm going to grab my 2.1 notes. 20 to 24, I think this had to do with age information below. So it had to do with ages. This is the information that we had in our notes. And what I did is I put it up here for us so it'd be easier. Okay, so we can see that the frequency goes up to 5. So I'm going to label 1, 2, 3, 4, 5. That's as high as it goes, but my table goes a little bit further. And then over here, you'll see that I left you this little blank space. And the reason why I did that is because our classes start at 20 to 24. We don't start at 0. So whenever you do that, you can draw just a little blank, not a little blank, a little break, excuse me, a little break in the graph. And that just shows that you are not starting at 0. You're going to start at the number that you're going to use just to save space. So, and we're going to use the midpoints. And our midpoints were 22, 27, 32, 37, 42, 47. They went by 5s because the class width was 5. So 22, 27, 32, 37, 42, 47, 52, 57, 62. Okay, and the first one had a frequency of 3, and then a frequency of 5, and then a frequency of 4, 4, 4, and then 3, 3, 2, 2. So I'm gonna finish my labels here. I probably should have done that before I started drawing, but this was the ages from our data set. This over here is the frequency. Did not give myself enough room to write the frequency and the ages. Over here, remember that break in the graph because I'm not starting at 0. So how would you describe this distribution? It's not as extreme as some of the ones that we saw, but I would call this, give me a highlighter to show you, I would call this a right skewed. So you can see here's kind of our peak up here. So it goes up to the peak, and then you can see it just kind of goes down. So it goes up to a peak and then starts to trail off. And so this would be the peak, this would be the tail, and so we would call this a right skewed distribution.